A lot of things, maybe everything can be hacked, and I would like to explain you one reason. I would have one theme going through the talk, that is, you have to actually define what security is to be able to judge if you have achieved it, or you can't get what you want till you know what you want. Okay, I don't need to repeat this. All those new smart solutions make us vulnerable to cyber attacks, and we have to do something against it. But why is cybersecurity so difficult? And the main reason is different from probabilistic events like a flash of lightning, where you can calculate risks, where you can calculate probabilities, where you can learn from the past. In cybersecurity, we are dealing with an intelligent attacker, an attacker who can think about ways to attack the system which even the designer didn't think of. So I think that this threat of an intelligent attack is the reason why cybersecurity is so difficult. You cannot test if it is secure because you might not have the idea the attacker has. And furthermore, the attacks scale differently. If you have a bad lock at your front door, there might be some burglar coming in, but the burglar will not be able to attack 1 million doors. Whereas if you have a vulnerability in a software system which is widespread, like you can exploit it to make ransomware to get money from the people, actually cybercrime is more than a drug in means of money by now. So now, if you have one vulnerability in the software, you can apply it 1 million times and you can spread your attack. That's another reason why cybersecurity is so difficult. You cannot think about, oh, maybe one attack happening. It will be, if there is a vulnerability, it will be very, very, very widespread. Also, an intelligent attack, an intelligently planned attack, can have dramatic consequences, like cascading effects. If people would attack a smart grid, they would not just try to do something which looks like a normal event. They would trigger something which might have cascade effects and might yield a blackout. Also, cyber espionage is mostly undetected. They will not tell you if they got information about your new products or if they know more about your company to attract your best customers. And the main theme of this talk is that the main reason for insecurity is that most applications do not have a security specification. So we should not wonder that we do not reach security if we just use this one word like, oh, could you please make this power plant secure? Yeah, but what does this even mean? I will give you one example, a famous example. Actually, this is an Enigma machine. It's an Enigma K. You can see this in the Open Codes exhibition. There's an Enigma K there. And this Enigma machine was used, a machine like this, by the Germans in the Second World War, and they thought this machine would be unbreakable because it's so complicated. However, due to the construction and electric current not being able to fly, to go back and forth in the same wire, it was not able to encrypt an E to an E, or a B to B, or an A to an A. And back then, they didn't consider this a weakness because they didn't know what security is. But what you can actually do is, if you have a hint of what's written there, you can check it. Because if you compare the ciphertext with your candidate clear text, and there's one letter in common, then your hypothesis is wrong. It's a different text. And actually, this was used by the British to break Enigma, because if you want to break Enigma, you need clear text, ciphertext pairs to check if you found the right combination. And to find such pairs, they made hypotheses, like where's written Wetter or Oberkommando or whatever, and they checked these hypotheses by this vulnerability, which was not known to the Germans because they did not know what security means. If you ask cryptographers nowadays, they tell you that even if you can distinguish two clear texts by looking at the ciphertext, the system's not secure, and this is not reached by this machine. Privacy. We're talking a lot about privacy, and we're talking about a release maybe from a database, maybe you want to calculate some statistics, should not contain any personal information. But what does this mean? Actually, if I would release that one person in 8 took a shower, most law people will agree that this is not a personal information, even though I might name you the 8. But it's not a personal information because it's an information about the 8 people. It's aggregated information. However, if you then ask the same people, how about no one of 8 took a shower? This is personal information because you now know that every single one did not. And so to actually get privacy, we need a precise definition of what that actually means, what personal information is. And there is a definition. It's called differential privacy. And I would like to advocate that we should go to using this more than the classic definition that a database is anonymized if we cross out names. Differential privacy looks at the following. Imagine you have a database and you can calculate some statistics. This we will call a release. Now we cross out one person and calculate again the release. It might be slightly different. And this amount is kind of, the difference is kind of the leakage of personal information because we crossed out one person. It's the personal information in the release about this person. And now what differential privacy does is it looks at the universe of all databases and looks at the maximum difference you can achieve in the release by crossing out one person. And this maximum is the maximum that can leak. And if you now have a bound, you say, oh, this maximum is small, then you give a very, very, very strong guarantee, because then you know the release would not differ much even if I would not be in the database. So it's not about me. The blockchain. I claim that many proposed use cases of the blockchain are either insecure or nonsensical, because most people don't even know what the blockchain does. The blockchain gives you a distributed consensus, meaning all people have the same view on a certain distributed data. And now, if I tell you that this is what the blockchain does, you might think, oh yeah, that's nice, and people have a consistent view. But it's not actually what the blockchain does. The blockchain, at least the Bitcoin blockchain, looks at the longest chain. The longest chain was the chain made by the biggest computer power. The computer power is mostly in the hand of the honest people. That's the assumption of this Bitcoin blockchain. And now the longest blockchain is the true one, the one we all agree upon, because this is the one made by the most computing power. But that's not actually true, because you can extend the blockchain also by chance. You're looking for a solution of a certain riddle to actually prolong the blockchain. And you can solve this riddle by chance. So some evil guy might find the solution first, and whoops, the longest blockchain is not the real one. But a lot of other people will not see this and will continue work on the true blockchain, and then eventually the true blockchain will become longer and longer again. It will overtake this singular event that actually for a short moment the longest chain was not the true blockchain. But you have to know this to actually use it. You cannot really bet your life on the longest blockchain being the one you can rely on. It's actually that you have eventual distributed consensus, meaning something that's deep in the blockchain. This should be something we all agree on. Actually, how does now, if we want security definitions, how do cryptographers define security? And now I will be a little bit technical, but it's easy and intuitive, I promise. Okay, imagine you have a real system, meaning an online voting system or a system where you do online banking with, something which you would like to protect by cryptographic means. And now you can look at the input that's given to the system. It's a distributed system. And you can look at the probability distribution of the output given the input. And now we compare this, and this is how we define security, with an ideal functionality. The ideal functionality is, so to speak, the security specification. And now we would like to have that those two systems are not distinguishable, even if you know the input and know the output distribution. So the real system and the ideal system should not be distinguishable. But that's only the first step. The second step is that, unfortunately, we will have attacks, meaning there will be a real attacker compromising part of the system and maybe hacking part of the system and maybe deviating from the protocol there. And so we have to define what an attack means in the ideal world. And in the ideal world, it is that this ideal attacker has no influence on the ideal functionality. This is our security definition. The ideal attacker cannot change the functionality. But the ideal attacker can change the input of the corrupted party and change the output of the corrupted party. So this is something we cannot prevent. This is something we allow even in the ideal world. And now the security definition is, for every real attacker, there should be an ideal attacker such that the real and the ideal becomes indistinguishable. Meaning every evil thing a real attacker could do in the real world would also be possible in the ideal world, where the attacker has no influence on the functionality, which is secure by definition. And so we don't have to fear real attacks if they are as powerless as in the ideal world. So the ideal adversary is very weak. It can only replace inputs or outputs. And so the ideal model is secure by definition. And if the real model is indistinguishable, it's secure too. Now, cryptography is, to my opinion, a role model for cybersecurity. We should have definitions of security also in the other branches of cybersecurity. We should have a model. Which abilities does the attacker have? We should have clear assumptions what the attacker can do and cannot do. And we should have analysis or proofs that certain attacks, certain classes of attacks are impossible in the model. I think only with precise definitions we will have progress in cybersecurity. We need models, assumptions, and proofs. And then every attack still occurring will be something we learn from. We will learn that either our assumptions were wrong, we learned something, or maybe the model is not realistic enough, we learned something. So in conclusion, I claim most applications have no precise security definition. It is hence not clear if countermeasures work at all. Only if we define what security is, we can judge to what extent we achieved it. And cryptography, I think, serves here as a role model. Thank you.
I think the next steps fits perfectly to your session, Jörn, to your talk. It's in English again, and I'm very happy to announce our next speaker who has come to Karlsruhe from Belgrade in Serbia. I recently visited and had a 2-day tour through the vibrant Serbian tech and digital ecosystem. I was blown away. I was particularly amazed by the work of the Department of Physics at the University in Belgrade. So please welcome Dimitri Stepanenko from the University of Belgrade, who will show that the best solutions to complex problems come from nature. The Tesla Cam takes advantage of biological complexity and creates unique and non-repeatable structures that can be used as label for individualized protections of documents, banknotes, credit cards, and etc., which are impossible so far to duplicate. Come on stage.
Okay, so as you see, our idea is to use some piece of nature. In our case, it will be butterfly scales. So we will learn what butterfly scales are as unclonable tags, something that cannot be duplicated. So this is basically the set of things that we will talk about. So the previous talk explained that in the world of information security is not a sure thing. We're not sure how to define it, how it works. There are open issues, and we have a lot of mathematical knowledge to analyze those problems, and still things are not clear. With natural objects, things are a bit worse. So we try to solve a problem that's sort of worsely defined. It's not as defined as a problem of cryptography. So one of the problems of physical security is that if you can make the thing once, you usually can make it many times. If you make a physical forgery, if this proverbial burglar can make one key, he can, open one door. So we need keys. But if this proverbial counterfeiter learns how to make, how to print 50 euros notes, you will have millions of them. And this is probably as bad as somebody entering every computer in the world. So what we find here is a sort of solution to the problem of mass-produced forgeries. We will describe what the solution is. And I'm happy to say that this solution can be mass-produced. So I will explain how we produce this solution. It's still, how it can be made in vast quantity and still be secure. And in the end, have a great vision of the future. So what can it be used for? So I had to use a buzzword. Basic idea is that we want to have information about real things, about real objects. And this is one way to be sure that our information really corresponds to reality. So the buzzword should be Internet of Real Things. This is the story about security of information. We heard about it. So basic idea is that we want to store information securely. So we're sure that once we write some information down, it will never be changed by an attacker. We want to exchange it. We want to authenticate. We want to know who is the one who's changing information. We want to know where it comes from. and who are we sending it to. We need to verify identity of parties we're talking with. And also, we don't want somebody to listen to our communication. So all of this has some definitions and some solutions in the world of information. Now, basic things are coming from encoding information where we need to exchange it, being able to read it back. And idea is that whoever wants to do the same thing as we do need to solve hard mathematical problems. We have roughly idea what mathematical problems are hard and make attackers solve a hard problem in order to do his job. And there's a separate class of this sort of algorithm that protect information that actually also comes from nature. It's called quantum key distribution. And it comes from a property of natural objects, quantum natural objects. And somehow nature to quantum mechanics can solve this problem for us. It solves good part of problems with secure information exchange. This is one real system that it does quantum key distribution to solve some of the information problems. Now, what happens with objects? How we protect object from being corrupted or being copied? And the industry that dealt most with this problem is security printing. So usually place to find good ways to label objects, make them impossible to copy, is to look at your banknotes that you carry around and, or look at your credit cards. So here are two examples. One is, okay, my favorite hero, it's Leonhard Euler on a 10 franc banknote that never went into circulation. So it was designed. And now if it was very perfect resolution, if you looked close to this banknote, you would see some interesting things. Oops, sorry. Okay, this. So if you look at how are these things printed, so let's say look at this polyhedron. So one of Euler's famous results, you will see there are some really fine lines on it. There are some really fine lines on Euler's face, and this is technique of preventing counterfeit that's a few hundred years old, because you print it very well. You need to know your printing trade so well that the attacker cannot print something with the precision requires to copy this. Another example is a dove. It's a hologram on Visa cards. And there, okay, security comes from that it's a hologram. You cannot make holograms at home. That's the idea. However, the set of things that are used here is growing. So security of labeling physical objects goes on putting more and more technology into it. So if you just look at the modern banknote, in addition to these very fine lines, holograms, watermarks, you will see, I don't know, you will see so many things. So for example, if you ever look at any banknote under UV light, you would be surprised. So it doesn't look the same. So then the battle to protect items from counterfeiting becomes a battle in who has better technology. And it's usually, again, as in a cyber world, in real world, you don't know how clever your attacker may become. So one solution for this problem is to make every object distinguishable. So instead of making many objects, you want to have a different security element on everything. Because again, the problem is, if they are not, once you know how to print one banknote, you will know how to print many. So this is image from a website of a company that sells security printing machines. And in this case, it's printing packages for medicine. So this printing cannot be done by anybody, but as you see, it's printed en masse. So there are many boxes for medicine that are printed on this line. And of course, if an attacker comes with his own machine is in his garage, they can make many boxes. So again, to protect items, we better make each of them different. And now we go into nature. When you look at the things around you, you usually don't see many copies of anything. So proverbial things are fingerprints. That's the first thing from nature that was used as if every fingerprint is different. So basically, each one of us carries, 10 or less distinct tags on two hands. And if we were able to attach a fingerprint to everything, it would solve the problem. Of course, we cannot cut people's fingers around, so we need to find a better solution to this. But usually, if you look at the nature, you will find many patterns, arbitrarily complex and arbitrarily complex looking. So if you like to walk around in the woods, you will see that every tree is different, basically everything from nature is different. The problem is, again, trees are also a bit clumsy to attach to things. And we were looking at something that will help us. So we need a structure that both is complex and looks complex. It's important that it looks complex because, again, we need to compare our secure tag with our database. And we need to look at it. And also, the part of it that we see routinely should be complex. So this is our solution. So one of the parts of nature that look beautiful are butterflies. So you see that they have vibrant colors. They look great. So this is probably the most popular and considered the most beautiful butterfly around. It's called Morpho. It has beautiful blue color. It has many shades of blue color, and also it changes colors as you look at it from in different directions. This is how it looks. And you will say, okay, there are many different colors in the natural world, but then you would get surprised. So if you look at the material that this butterfly is made of, it's transparent. So basically, if you just take all the material from the butterflies, make it in a single slab that's completely homogeneous, and look at it, it will be transparent. It looks like plastic. So these colors don't come from pigments, like any colors that color our clothes or paint our walls. These colors come from structure. The idea is that, okay, you probably saw similar effect if you ever saw a puddle of oil on the rain. So if you look at it, it looks like rainbow. So edges of it have different colors. The trick is that the structures that have the size that's the order of the wavelength of light, so let's say 100-ish nanometers, they appear colored. Colors on the butterfly come from similar things. So on butterfly wings, there are structures that are of similar size and appear colored. So, and these structures are scales. And now, scales are something that you probably held in your hand if you ever caught a butterfly. So there's some dust, looks silvery dust on your fingers that butterflies leave behind. So each speck of dust is a scale that's part of a butterfly's body. It looks like a little plate around 100 microns long, around 10 microns wide, and around a few microns thick. And it has very intricate structure inside. So this structure is modeled here. So as you see, so this thickness is few microns, and there's a lot of structure inside. You see these things? These are two different kinds of butterflies with two different kinds of structures. In this one, it is like sponge inside. And the color that you see when you look at butterflies depends on this structure. If you want to replicate this color, you need to replicate this structure. And this is hard. So basically, you need engineering that will shape your material on the scales of tens of nanometers and in 3D. We think that it's impossible, and therefore each spec is unique and clonable tag if we can recognize one as this, and that we can. Another question is how complex these things are. So this is how one scale looks under microscope, and you need to guess how complex this thing is. So can you make a copy of it? So if attacker cannot make scales, his best strategy would be to look through all the butterflies in the world, look at all the scales, and trying to find one which can replicate the one he's trying to forge. And then we did some calculation and calculated how many scales should this attacker test. And as many things with combinatorics, huge numbers show up. So number that really looks good is that if you take every atom of our universe, place another universe in it, and make every atom in this superstructure a scale, then, and only then, you will have appreciable chance of finding another scale that will do the job. So then, basically, it means that if we pick one of these and attach it to a item that we want to protect from the forgery, and also we are able to recognize each of those, then we're safe, for some definition of safety, of course. And this is what we do. So basically, we have pushed to technology part of it. So we have a little farm for butterflies, already small. So it's a size of 1 cubic meter, and we can grow butterflies for it. So it sounds good. Basically, it's the second insect that was farmed for purposes of en masse. So on large scales, if 1 cubic meter is large scale, the other one was silk bug. But also density of these things on butterflies is huge. So as you remember, it looks just like a dust. So, and there are around 100,000 usable scales on a butterfly. And then if you made, say, 1,000 cubic meters farm, which is less than the volume of this room, you would be able to, say, put one scale on every banknote in circulation. So it's doable to produce them en masse. Of course, producing them is not enough. You need equivalently fast way of attaching them to things, and that's another thing that we developed. So we know how to farm the butterflies. Then it's like taking wool of the sheep. We take scales of a butterfly, and it is also possible to put them on objects in a process that's very similar to printing. So we can print cards. We have a few thousand cards of this shape that look quite flimsy. Okay, I have one. But they're actually things that we hope are the most impossible things to copy. Okay. Looks like this. Security element looks like just a little gray smudge on the edge of the card. And our great vision is to use this to secure everything. Basically, we can use it in standard problems, so we can protect banknotes, credit cards, and everything that's being protected by security printing. But the idea is also to secure entries into any copy of the real world in a world of data. So we know that our data are correct at the entrance. Okay, so thanks.